Okay, so welcome back to the last lecture of the course. And this lecture will be about applying these ideas that we have now done all back into the random transposition shuffles. And I'm not going through all the details because the problem is at one point in the proof we have to go into really understanding some very deep theorems about representation theorems of the symmetric group. But I will reduce to that setting that it becomes purely an algebraic question and combinatorial question at the very end. So on the other side, the Fourier analysis allows you to do it in this completely algebraic question that we want. So let's do this. So a random transposition shuffles. So remember that a random transposition shuffle I mentioned in the very beginning. So if you want to go back to the very first lecture, actually, I think in the course, I mentioned the random transposition shuffle, which was this idea that you take the deck of cards. So this is like, let's say, 52 cards. And you take two random cards here. Like, let's say, I don't know, let's mark this with like some color. Maybe use another. This one and then that one. And you swap these two cards. So this is a transposition. So what we especially want to define is that the random transposition is that you choose randomly these two positions. And if you choose the same card, you don't really swap anything. So that's the kind of thing. And does this so this model there's these randomly chosen positions. Model this random walk using this mu. So this is a random walk in this symmetric group of 52 elements using this mu, which is a probability distribution defined by, I think I mentioned this already, that you have this 1 over 52 when the permutation is the identity permutation. It's 2 over 52 squared when this is a transposition. So you go through all the possible pairings that you can have, and then you have the probability, you put the uniform weight of being equal and chosen, and this otherwise. So that's the probability distribution here. So this is a mu on S52 to 0, 1. And what we would like to prove is this theorem. So I state the theorem in this way, that if n is at least 270, then if you take the self-convolution of this to the uniform distribution, this is uniform in S52, which is the uniform probability, then this is at most 1 over 100. You can actually get it to exponentially small in n. There's a spectral gap, but in particular you get this, that after 270 shuffles you are this close always to the uniform. So that means, remember that e.g. that if you take the random walk, which is given by this, then after 270 shuffles, the probability of the corresponding random walk in the group being inside A, and then that's take the A over the the F52 factorial, which is the size of the group. This is less than 1 over 100 for any A in the S52. So if you have any possible combination of shuffles, this becomes after n we have this by the definition of total variation distance. The xn is the random walk generated by the mu, which is the IID process where at every stage we choose a random permutation given by with the probability distribution mu. And now the outline of the proof of this theorem is given by using the upper bound lemma as follows. So what we need to do is that we need to basically compute the Fourier transform. So the upper bound lemma, so let's prove outline. So the upper bound lemma gives the following, that if you take, again, it's actually in this case, I'll take this 4d mu star n lambda squared, so just because I don't want to write the square roots and the multi here, this, the upper bound lemma is just basically saying the following, that if you open this up, this is just equal to the summation psi in the S52, the dual group of this, whatever this actually is, this is the hardest part to understand this, that not equal to the 1 corresponding to the trivial representation, the dimension of weak psi, and then you have the mu Fourier transform of this psi to the power n, and take the Hilbert-Schmidt norm of this at the point psi and this square. So that was the upper bound lemma. So if you want to understand the upper bounds for this, we just need to actually understand what these numbers are over here. So what turns out to be, so what we can do in the following, so let's compute the Fourier transform. So that's basically what we need to do over here. So we need to kind of understand these two quantities, what are the permutations, but in actually proving the decay, it's really this Fourier transform that is important to compute. So what we can do is that let's first of all compute this Fourier transform. Let's try to find out what kind of matrix it becomes. So first of all, what we can realize in the very beginning is that if we have a permutation, so if we have some permutation, let's say gamma in S52, so any shuffle basically, then this implies that for any sigma in S52, we have that this mu sigma is equal to the mu inverse of this sigma and gamma. So the measure is kind of invariant under this operation, and that's because of the nature of transposition. That if you take any two permutations of gamma and sigma in this way, then you preserve the same value. So let's say, for example, if a sigma is a transposition, then if you take this conjugation with any permutation, you still have a transposition, because you're first permuting with something, then you have a transposition, and then you invert the previous permutation in the back. So you still have a transposition, which possibly might have swapped the order, but you have the same weight on this. So we have this kind of identity thing going on. And then this implies that the Fourier transform, once we compute this, if you open the kind of expression, we can actually prove that this satisfies, or let's open the definition. So it's just summing over all the group elements S52. That's the definition of the Fourier transform. I can put this mu sigma and then rho sigma, and this at the point, I think I'll take it at the point sigma. That's the definition of the Fourier transform. And then once I open this up, I can actually put to the both sides this expression, replacing this with that quantity. So we have sigma in S52, and then you have the mu gamma minus 1 sigma gamma, and then you have the rho psi sigma. Okay, so that's the expression we get in this way. And now you can use the fact that actually this psi has this homogeneity property, so we can actually apply this in this way, that sigma in S52, we can open this whole thing up. So what we can do here is write this in the following form, where we are taking this mu gamma minus 1 sigma gamma, and I can take inside here the expression. I think I take rho psi. I want to put here some element. I'm just doing this in my head. So we have gamma minus 1 sigma gamma. So we have a gamma here, and then we have rho psi of gamma inverse. So this is the remember that this is a homomorphism. This is as the rho psi is a homomorphism. That was the definition of a representation. It's a homomorphism, so it satisfies this property. So now I can take this matrix outside in the front, so I get rho psi gamma, and get this summation sigma S52. I get mu gamma minus 1 sigma gamma, rho psi gamma minus 1 sigma gamma, and then I get rho psi gamma minus 1 in the outside in this way. So I just proved, because this is a bijection, this actually sums the whole space completely outside. So what I have proven now is that this is equal to the Fourier transform. So I actually obtained here the Fourier transform of the psi, and then I have the rho psi gamma minus 1 as here. So I just proved that the Fourier transform satisfies this kind of property. I haven't computed it yet, but I actually proved this kind of a property that I have here. And why is this important is that this implies that this Fourier transform as a mapping, so this, remember that it's a linear map, this is a morphism. This is the definition of the morphism, that it's if you take it from the both sides, if you take the inverse outside here, because as the, well, if you have this this expression, if you take this mu psi, and this is rho psi gamma, mu Fourier transform, and rho psi gamma inverse, then this is by definition equal to rho gamma inverse. So you can multiply it on the both sides. So this implies that if you multiply it from the right, we get the Fourier transform psi of rho gamma is equal to the rho gamma mu. So as this is now true for every gamma in the S52. So it's a morphism. That was the definition of the morphism as a mapping. So since this psi, or this rho psi is irreducible, remember that this set, actually, if you have a morphism from the vector space to itself, and if they're irreducible, so these are irreducible representations to the unitaries group of the weak psi, Schur's lemma implies that this Fourier transform have to be equal to this k, some psi, let's call it k psi, of the identity matrix at the vector space psi. So this is, let's call it xi. So this is identity in weak psi for some constant k psi, which is a complex number. The Schur's lemma was saying exactly this. You have a morphism and your irreducible representation. Because it's irreducible representation, the only way that this can happen is that this morphism is a constant multiple of the thing. So now if you take the trace, of this in the vector space mu psi, we get that this is just equal to the dimension of the vector space times this kappa psi. That's the definition of the trace once you multiply all the operations. But on the other hand, I can compute the trace from the other perspective. I can actually compute this just using the linearity. So this actually, if you compute this is equal to, by definition, this is equal to the, if you sum over the whole group S52 and mu sigma, that's the trace of the weak psi, and then rho psi of sigma, rho psi of sigma, yeah. I'm just basically using the Fourier transform, then using the traces being linear in this sense, so I can put it inside, so I get this into this expression. I want to just basically compute from the other side and then realize what this kappa actually becomes. So once I open this whole definition up, then because this is supported on transpositions and the identity elements, so we have this definition with the trace of weak psi, rho psi of the identity element, plus then the tau is a transposition. So we have then the other ones, mu tau, and the trace of weak psi, rho psi, tau. So this is all the transpositions that are remaining. Then we actually can then compute this, that as this mu e is equal to, so this is kind of what is remaining. This is always equal to 1 over 52. And we have that rho psi at the identity. This is the identity matrix, which implies that the trace of the weak psi of rho psi e, this is equal to the dimension of the vector space. So that's just, I'm looking at this term. This implies that we have that the first term is equal to mu sigma trace of weak psi rho psi e is equal to 1 over 52 dimension of the vector space. Okay, so that's the first term. And then what about the second term here? How would we analyze this? Well, now you can use the fact that the transpositions have the same measure. So if this tau and tau prime are transpositions, then this implies that the mu tau is equal to mu tau prime, which was equal to 2 to the power 52 squared. So this is just summing constants. And also we have that the traces, because if you have different transpositions, they actually you can prove that the traces, rho psi, they generate the same number. So you get actually the same traces in the case of the t prime rho psi t prime. So we have this and that being the same numbers. So we can just, if this n is the number of transpositions, so I can then compute this. This is just the number of transpositions. You have 52 cards and you have the two possible choices, so it's 52 over 2. And then you can compute that if you take the 52 over 2, this is 51 times 52 over 2. That's the by computing the transpositions. So now this implies that if you take this expression that we have here, so this over here, because they are all the same constant, this expression over here is then equal to, this is equal to this number of transpositions, which I will put there in a second, then this 2 to the power 52 squared, which is the unique measure, and then the transposition, I put here trace of weak psi of rho psi of transposition for some t psi, for some fixed transposition tau psi. I mean, it's the same constant for all of them, so that's why I get this equal to then 51 times 52 over 2, and then you have the, actually if I put everything in the front, I get this into the divide by 51 out, so I get 51 over 52 times the trace of the weak psi, rho psi, tau psi. So now we have proved that the Fourier transform have this expression. So we have proved that we have this expression coming from that sum, and then for the other sum we already proved that it was this expression for the other sum over here, what we have here. So adding these two together gives you, by this as we did before, the trace of the Fourier transform, which is the dimension of K. So we can compute the kappa psi, which was equal to that, gives you the Fourier transform. So combining all of this, if we combine all of that, we now have that the Fourier transform is equal to, well, this was this kappa psi of I psi, and by that computation, because it's this basically this constant and using the trace, once we do the computation, we have that this is equal to 1 over 52. That was the expression, because remember that there was the dimension in the front, so there was the dimension of the vector space front inside this this expression, dimension of vector space here. So once you take the trace, we get this 1 over the dimension of vector space disappears, so then you have 1 over 52, 1 over 52, and then times the trace of v psi, and we have to divide by the trace here to be able to get it into this form. Divide by the dimension of the vector space, and then you have the I psi. So that's the kappa that you get in the front, if I did this correctly now. So now this is a concrete expression, the Fourier transform of the probability distribution given by the random transpositions. Okay, so in particular, this implies that now if you take the power, that this mu star n, this is equal to this kappa psi to the power n I psi. So this is the kappa psi. And we see also that if you take the Fourier transform of n to the power n and take it adjoint, well, this is basically identity matrix times constant diagonal matrix, so it's adjoint to itself. So this adjoint becomes the same as the Fourier transform to the power n, so this becomes the same as kappa n I psi. Which then implies that if you take the trace of the Fourier transform of psi to the power n and the Fourier transform of psi and its adjoint, remember that this was in the definition of the Hilbert-Smith norm, this becomes then just the trace of these operations. So we get actually coming completely out, we get that this is equal to the dimension of the vector space v psi, because it's k to the power 2n, so we have k kappa 2n as the trace. And if you remember that this expression, what we have here, this was equal to the mu psi n squared of the Hilbert-Smith norm at the psi. So that was the expression we wanted to actually compute in the end anyway. So that's where we are now. Okay. So now we have now proven using the upper bound lemma that we got this upper bound for the uniform distribution. This is bounded from above by the if you use the upper bound lemma psi in S52 bound and then psi not equal to 1, and then you have here equal to the dimension of the vector space. You get that now squared because you have that twice in the front, so that becomes squared, and then you have this kappa psi that I have defined above here, and that to the power 2n. Okay, so now in order to bound this kappa psi from above, we just need to now then really compute these traces of these representations that we have in the definition. And that's where I want to stop now the lecture. So I don't want to go in further into this, because now it would go into really would need to understand the representation theory of the symmetric group. So in order to actually compute these traces of these irreducible representations and also the dimensions of these representations to be computed, we would need to then use something called Frobenius theorem from the representation theory of symmetric groups, which allows you to compute these traces in a very nice expression using something called partitions of integers into sums. And that requires its own like topic and going into the like bounding this and everything. And I don't want to now go into that, and I want to kind of end the course. And if you want to find more about how to do that, so I have some reference in the lecture notes on the literature that where this is done. But you can kind of like already now see that, okay, this is really this theory of like the representation theory, going to Fourier transform, allows you to basically reduce a lot of this theory just to understanding what kind of representations you have in the group. In the case of the ZP, what we started from the course on, that was really like quite easy to actually do the things. You just use complex numbers in that situation. So now this just reduces to these a bit more complicated topics that you want to have in this space. So thanks everybody for coming to this course and following everything, and I hope you got something out of this course, and looking forward to see you at some point later. So thanks a lot and bye.